went to the lunch club with the light mathematical flavor. And today we are starting this book by Fulton, Algebraic Topology. No, what is it? Yes, Algebraic Topology. And we have already covered a part of it. But for some strange reason, I would like to go through this part partially again, because I will need several points to be made and several notations to be fixed. Okay? Well, first of all, I would like to start with a very general overview of what we are going to do and why this is important and what is the main, say, point of the first, at least, part of this book. And the main point of the first part of the book is actually the Poincare theory. Or better say, Poincare formula. It goes as follows. What is what here? Omega n is an n form, locally written as sum omega I1 In dx I1 dx In with these coefficients, smooth functions. So this means that I assume that we are on the, say, n+1 dimensional manifold. So there is a smooth structure of the manifold. So the differential of a manifold, the differential of a form is an n+1 form. This is n+1 form. It can be naturally integrated against an n+1 dimensional submanifold, or domain in n+1 dimensional submanifold. And here everything is okay. This is an n form, and this is the boundary of this manifold, or say, of this domain, boundary of this domain. And the boundary of the n+1 dimensional domain is n-dimensional domain, and n form can be integrated against an n-dimensional domain. So actually this is the main result around which we are going to dance. And let me put it this way. The smooth structure plays a very important role in this formula, because we are prepared to differentiate the form. We are prepared to differentiate the form, and the very notion of the form is impossible without a smooth structure. We need to understand what are tangent spaces, what are cotangent spaces. So this formula is very heavily dependent upon the smooth structure. However, this formula also has a very good say, topological meaning. And topology enters this formula in this part. This is an n+1 dimensional domain, and this is the boundary of this domain. Let us try to do the following computation. I'm taking an n form, integrating it around an n-dimensional. This to remind you that manifolds are assumed to be oriented. There is a notion of orientation of a manifold. But I would assume that this form is closed. Meaning since everything is recorded, I better write everything without bad errors. Meaning that d omega n is 0. And we also assume that omega n is closed, but in different way. Meaning that the boundary is empty. No boundary. And we want to consider this expression. And we want to ask the following question. How can I change the form and how can I change the integration domain without changing the value of this integral? So I want to say, to repeat again, that we always assume the form to be closed, the form and the domain to be closed. And the question is, what is my freedom in changing the form and changing omega that will not change the value of this integral? Let me see that there is some change. For example, if I take omega n and add differential of some other form, differential of some other form. This other form has to be n minus 1 dimension. And try to integrate. What will happen? This part is going to remain as it was. And as for this part, I can apply that formula with n replaced by n minus 1 and get omega n minus 1 d omega n. But what is this integral? It is 0. Why? Because there is nothing to integrate over. So I'm free to add such form, a differential of a form, to the closed form I have already. So actually, what this really depends upon is not the form itself, but rather its class modulo the differentials of forms of lower order. So actually, again, this expression depends upon the class of forms. On the other hand, imagine that I do the following. I take this manifold and add a boundary of a bigger manifold. What do I get? Definitely I have the following I had before, plus, as for the second integral, what can I do? I can again use exactly that formula and get d omega n plus 1. And what is it? It is 0. Why? Because the form is closed. Correct? That means that this expression actually depends not on omega n itself, but rather on this manifold modular a boundary. Modular a boundary. So this means that we have a pairing between the classes of forms, modular differentials, and the classes of submanifolds, modular boundaries. One can prove that this pairing is non-degenerate. So if this is non-zero, so if this is not a boundary, if this is not a differential, then you can find something to integrate it over and get non-zero. And on the other hand, if this is not the boundary, then you can find a form, a closed form to integrate this form over this and get non-zero. So actually, the classes of forms and the classes of, say, submanifolds are in a strange duality. But let us analyze this duality. It is called Poincare duality. Let us analyze this duality. The right-hand part is a purely topological object, isn't it? Because the only thing we are going to deal with are domains and their boundaries. And they can be defined in purely topological terms. The left-hand side is dependent upon a smooth structure of the manifold, because you cannot talk about forms without differentiability. Actually, what it says is that though this object is dependent upon, seems to be dependent upon the smooth structure, but actually it does not. You can change the smooth structure without changing the topological structure, and the set of this quotient space is going to remain exactly the same. And now the names. The set of classes of equivalence of n forms, of n, say, domains, n-dimensional domains, n-dimensional submanifolds, modular the boundaries, is called the homology, nth homology class. The class of n forms modular differentials is called the nth cohomology class. Nth cohomology class. In this book, the first part of this book, the first chapter at least, is completely devoted to the two-dimensional version of this, which is being studied in great details. And the author also goes to some very striking and very effective applications of these ideas. And in the last couple of chapters, Fulton outlines the multidimensional generalization, but actually I have already shown what this multidimensional generalization is going to be. Certainly it is up to a very precise definition of what are forms, what are boundaries, and so on. You have to do this, but nevertheless, a model of that it is. So, okay. I want to say something more. Okay, that. I have already mentioned that this pairing between homologies and cohomologies is non-degenerate, and I explained what this non-degeneracy means. In fact, that means that, well, we can consider the set of quotient classes, modular boundaries, as a group. There is an actual group structure there. And we consider the set of even a more natural group structure is present here. Actually, not only group, but say linear structure is present here. And the non-degeneracy of this form, the existence of the non-degenerate form, means that the ranks of these groups or the dimensions of these spaces are the same, which is a very important, really important fact, that the dimensions are the same. Then there is a huge, say, field called differential topology, which deals exactly with this kind of problems. We are considering, say, a smooth manifold. We are using tangent, cotangent bundles on this manifold to construct various quantities associated with this manifold. And then very often one can show that these quantities are in fact topological invariants. Though they, in their construction, one has to use the smooth structure, but the result does not depend upon smooth structure. And there's a number of very important characteristics that can be obtained this way. So I think I said everything I wanted about the general idea of a huge part of this book. And if there are questions, I would try to answer them and then move to a very systematic covering of the material of this book.
Would you say the meaning of non-degenerate again?
Okay, this means if is not zero, that means if omega f is not some differential, then there exists omega n such that, if you wish, omega n, omega f n is not zero. And vice versa. If omega n is non-zero, meaning if omega n, non-equal by the way, omega f is not the boundary of some phi, then there exists omega n such that this is non-degeneracy. Other questions? But the Poincare formula is definitely the heart of the matter. Okay, so let me descend to a two-dimensional space. This is not the best space for me. It's not enough space there. But we have to.
Well, you can put it on the blackboard.
But on the blackboard, it is good on the blackboard. And I want to go through. Again, the first part is pretty easy. But I must say it is done quite well. I have to apologize, but I need to keep the book. I did not know that I will be taped. Okay. So from now on,
You'll send your lecture to Fulton.
yeah. From now on, we are going for some time to live on the plane. Sorry about that one. And you will always be an open subset of R2. Though it is not necessary, it means that if I take any x in U, I can surround it by a small disk, and the disk is still in U. So I'm free to go from any point in any direction for some time. Okay? All functions, say R, C, are assumed to be smooth. We are not going to talk about other functions, though a lot of these results are actually valid for under much less restrictions. Smooth means that all partial derivatives exist and are continuous. Partial derivatives of all orders exist and are all continuous. By the way, if we have one dimension, then if there exist derivatives, then the function is automatically continuous. This is not the case in two variables. You can have functions which have all partial derivatives but they may be discontinuous very well. So the notion that all parts of the groups are continuous is an important one. Okay, now F is called locally constant if it is locally constant. What does it mean? If it is constant near every point, in a neighborhood of every point. How many locally constant smooth? Again, functions, all functions are smooth. There do not exist any non-smooth functions. It is, well, a magic phrase here. All functions are smooth. How many locally constant functions we can construct? Say in this domain that I have drawn. Well, one-dimensional space, only constant functions, locally constant functions in this domain are locally constant. Correct? And let me explain this in more details, but this is really very easy. A function is locally constant, smooth. Is locally constant if and only if it is f is constant on every component of U. Component means a connected component. By the way, should I explain what connected means? I should. Okay, definition. A set is called connected if it cannot be represented as a disjoint union of two open subsets, non-empty subsets. So, say this is a no. This set is not connected because it is non-empty disjoint union, open non-empty subsets. Well, what is open? The question is what is open? Open in itself, that means that you can surround the set by an open set. The set is open in itself if it is the intersection of a really open subset with this set. Okay? But since our sets are all open, then then I do not need. Then the open subset is the usual open subset. Am I clear or not? Okay. Okay.
You're avoiding the word closure.
No, the thing is, if my set is open by itself, that means for every point there is a small disk still sitting here. Then open subsets of this set are simply open subsets in the plane. Simply open subset. So this set consisting of these two parts is definitely not connected because this is open, so they are disjoint. It is the union of two disjoint open subsets. Well, definitely you want to have a small theorem which will be needed. And open set is connected if and only if any two points of U can be joined by, say, a smooth curve in U. I think this is more, say, geometrically related to the notion connected. I want to do, this is a simple fact, but I want to prove it. But the openness is important. If you do not have open, then this is not true. Okay. If the set is not connected, then I can choose a point in one set, in the other set, correct? And there is no way that they can be connected by a smooth curve, which is in U, obvious. Because they are both open, they are disjoint, and the curve, there is a simple fact that the curve cannot be, I skip this argument. The thing is that I want to prove that if the set is connected in this sense, then any 2 points can be joined by a smooth curve. That's what I want to prove. Let me first do a hand waving work of this. Take 1 point and consider all points which can be joined to this by a smooth curve. So all reachable points, all points where I can arrive on a smooth train. Okay. Let me assume the opposite, that there are 2 points which cannot be connected by a smooth. Let this be connected, and these 2 points cannot be connected by a smooth curve. Then the set of all points to which I can come from this point does not include this point. But the set of these points, reachable points, is an open set. Why? Because if I can reach this point, then I can reach any point in a neighborhood of it. Correct? Can I reach this point? Yes, I can. Just reach this and go here. And if you are worried about non-smoothness, it is not difficult to smoothen this part of the path. Correct?
Sorry. How do you know the boundary doesn't go smack through the point?
Because the set is open. Boundary is not a part of my set.
Well, you just made a boundary. You created one. Then it's not part
No,
of the
it is not a, no. It's just, I should not have drawn it as a boundary. This is the subset of all points reachable from this point. So if I have this point, then there is a small neighborhood of it still. There is a small neighborhood, and all points in this neighborhood still can be reached. How? Reach the center and then go to any point by a straight line.
The point has a neighborhood because
Yes.
it's an open
Yes,
set.
yes, that's
and any point in the neighborhood can be reached. Yes.
Yes. Then, on the other hand, each non-reachable point, the set of non-reachable points, is also open. Because imagine that this is a non-reachable point. I take a small neighborhood, and I can reach any point in this neighborhood. Then can I reach this point also? Reach this and go here. So the set of reachable points is open, and the set of non-reachable points is open, and they obviously do not intersect. And we've got this splitting into 2 parts. So this is hand waving, and I think this hand waving is enough. Is it? Hand waving can be very...
I think it's enough, but that non-reachable set might be a closed set.
No. Yeah, I proved that actually it is both open and closed. But open and
One of those.
yes, no. The set can be both open and closed. But what I'm talking about, it is open.
But you pick the point in U, which is open.
Yes. Yes. So the openness is important. Try to do this kind of consideration for a non-open set, and you get into trouble, and the assertion is simply not true. The notion of topological connectedness and, say, pathwise connectedness are different, even in two dimensions.
The code that you skipped actually is valid without openness. So in one direction.
Yes, in one direction it's definitely valid without openness, and in the other direction the openness is very important. Yes. Okay. See? A smooth f is locally constant if and only if its partial derivatives are equal to 0. Obvious, because partial derivatives are local notions. If the function is locally constant, then as far as it concerns partial derivatives, it is simply constant. And we learned long ago that partial derivatives of constant functions are zeros. In the other direction, if the partial derivatives are 0 everywhere, then it is, and the set is open, then it is constant. Then the function is locally constant. So this means, the first means that the function does not depend upon x. The second means it does not depend upon y. So it does not depend upon anything. It is locally constant. Okay. So the set of locally constant functions is actually the following. You, instead of considering the whole set, you consider the set of components, and you have to fix a value for each component. The function is constant on each component. Okay. A small corollary. Open U is connected if and only if dxf equals dyf equals 0 implies f is constant. This always implies that f is locally constant, but if it is globally constant, that means that there is only one component. Because if there are two components, you can choose values on these components freely. But this is already some kind of topology. Connectedness is definitely a topological notion. And here we formulate the topological notion in terms of the smooth structure. Now, a differential 1-4. Fulton suggests that we look at it in a very simple-minded way. So, differential form omega 1-4 is b of xy dx plus q of xy dy, which is true, definitely true. But he wants to say, okay, this is actually a form is a pair of functions, which is true. But as physicists know very well, it is important how does it transform under, say, diffeomorphisms. And actually, if you want to define a form, you must set how it is being transformed under diffeomorphisms. But for the purposes of these initial chapters, this definition is good enough. I want just to take a couple of minutes to define maybe the notion of the form a bit more precisely. Okay, we are living in omega. Yes?
To talk about diffeomorphisms, you need geometry. Do you need geometry to this form?
No, forms are only need a smooth structure, and I will explain it right now. You see, take any point here. You see, this is a plane space. And plane space introduces, this is a plane, so it is a flat space. And flat space introduces some undesirable identifications between the space and the tangent space at this point. But let us better do it this way. Let us simply glue a two-dimensional linear space at this point. Say that this is the origin of this space, and vectors in this space are called the tangent vectors. Okay? So we have a tangent space. Actually, to understand what is a tangent space, it is better to consider not a plane, but say a sphere. If you have a sphere, then at each point of the sphere you can draw a tangent plane. And this point at which it is attached to the sphere, you call it the origin, and you have tangent vectors in this plane. Simply here, all these objects simply collapse. Now we want to have the notion of a vector field. That means at each point we choose a tangent vector. At each point we choose a tangent vector. Definitely we want this tangent vector to change smoothly as we move from point to point, and one has to explain what does smoothness mean, but you, in this simple case, it is not a big deal to understand what this smoothness means. So, a vector field can be locally written as the following. Where ddx is the tangent vector. What is tangent vector? It is the velocity vector of a motion, correct? Tangent vector always should be considered as the velocity vector of some specific motion. I can move through this point parallel to the x-axis, correct? With speed 1. And the related tangent vector is called ddx. I can move through this point in the direction of the y-axis with speed 1, and the related velocity vector is ddy. Since these two vectors obviously form a basis, then every vector can be written as follows. Okay? So actually, if we have a notion of a tangent space, we have a notion of a cotangent space, the space of linear forms on the tangent space. The cotangent space is the space of linear forms on the tangent space. So linear spaces always live in pairs, space and the dual space. So cotangent space is... And actually, a form is a so-called section of the cotangent bundle. That means, at every point, I choose a linear form and a related tangent space. And dx, it must be a linear form, such that dx is 1, dx dy is 0, and similarly for dy. So actually, this is a decomposition of the cotangent vector in the basis dx dy. A decomposition of the cotangent vector in the basis dx dy. But again, since on the plane we have a globally defined coordinate system, x and y, we can, this globally defined vector system allows to identify everything we have. We have globally defined bases in all tangent spaces and all cotangent spaces. But the moment, just imagine that you are on the sphere, and you immediately understand that you can do this only locally. You can define the basis only locally. Okay, but there is another important thing why we want to write it this way. It is a reminder for us that we are going to integrate these guys. We are going to integrate forms against one-dimensional submanifolds. I hope I have not missed anything. Okay. Now, paths. Path is a smooth mapping, say AB, from the interval AB to the plane, actually to U. Smooth. Smooth mapping. So actually a path is a couple of functions, x of t, y of t, and these two functions are smooth. And the resulting point is always the problem is what is smooth at the endpoints. There are a million ways of defining this, and a nice thing is the following. Imagine that actually this mapping is extended a bit beyond A and B. Then the smoothness is complete. Understood. So if you have a path, you can a bit extend it here and here, and it's still a path. Okay. So the image of path is a curve in space, the image of path. But path carries more information than simply the curve. It is the parameterized curve. Path is a parameterized curve. Path is a parameterized curve. And then we can easily define the integral, actually, Fulton. You are not going to show this to Fulton, I believe. Because there will be some criticism and I don't want it. Okay. Fulton says this. Oops. Sure. If I have a form and I have a path, then I define the integral of the form the following way. T of x of t, y of t, dx of t, plus q of x of t, y of t, dy of t. From everything is well defined because all functions are smooth, so one can always integrate a smooth function over a finite domain, over a finite domain. But the thing is, this is an integral over a path, not over a curve. This is an integral over a path, not over a curve, because this parameterization comes in a very serious way. But one can prove that it is not that bad, that actually the right-hand part does not depend upon reparameterization, preserving the orientation. Maybe you write it down and I will explain. Actually, the right-hand part and therefore the left-hand part do not depend upon a reparameterization of the curve, which preserves the orientation.
Gamma was a curve or gamma was a path?
Gamma was a path.
And path
Just-
means a parameterized curve.
Gamma is a parameterized curve. Parameterized curve. And this is an exercise for Math 212, and it is left participants to do. One can easily prove that actually this is an integral of form over an oriented curve. Parametrization is important only as far as orientation goes. What does it mean? In this case, it is quite easy to understand what does it mean, orientation. This is gamma, and this is gamma of 0, I call it A, and gamma, not 0 of A, gamma of B, I call it B. So I want A, I can choose any smooth parameterization such that A is gamma of the initial point and B is gamma of the final. So for any such parameterization, on the right-hand part gives the same result, and therefore the left-hand side is well different. Again, these are all trivial things, but one has to formulate them in order to be able to move forward.
If you have a path, like, say if you have a path on like a sphere running from the North Pole to South Pole, and so you're going to pass through those points where the tangent planes are going to be vertical. So does that mean then all you have to do is just define the path to be so it's always smooth? You have to define it as a collection of parameterizations.
Okay, that's a good question. That's a good question. Let me explain. Imagine for a moment that we are not in the flat space, but we are on the sphere. Then the notion of a path, which is parameterized curve on a sphere, is well understood. It is exactly like this, but it is a mapping which point of t is on the sphere. The mapping is smooth, and it is not difficult to understand what does it mean, smooth. So, and this is a parameterized path. Then actually we can define this object also. How can we define it? We can switch the path into small pieces and define integration on each piece separately and then add them up. And if these pieces are small enough, then I can introduce the local system of coordinates over there and do exactly what I did before. Okay? Define it this way, and everything seems to be okay. But then, again, one has to prove the fact that actually this depends not upon the path, but rather upon the class of equivalent paths. Two paths are called equivalent if the set is the same and orientation is the same. Set the same and orientation is the same. But he does not mention it. Well, and here immediately we get something quite interesting, and this is the following. There are very special forms. Consider that I have a function, smooth function, and I compute its differential as we have taught where in the kindergarten. This is definitely a form, but a very special form, I must say. And let me try to integrate the form along a path. Then one can easily prove it is actually nothing else but the fundamental theorem of calculus, that the result is f of gamma of b minus f of gamma of a. If you are integrating this specific form against a path, that's what you get. What do you immediately see? Actually, the result of integration depends only on the starting point of the curve and the ending point of the curve. But it does not matter. What do I have here? Okay. Actually, this is a special case, the simplest special case of the Poincaré theorem, because I can write it as and this is a kind of integral. A and B is the boundary, so it's a kind of integral. Okay? But this is, say, one-line computation using the fundamental theorem of calculus, nothing else and nothing more. Okay. So, let me do some example. And this example was prominent in what Josh was talking about some time ago. I will do it a bit differently, but definitely all the main results are the same. I will study some very interesting function. This is the plane, and take any point of the plane and consider the polar angle. So the function is phi of t. You immediately see that this notion of the polar angle is ill-defined. Why? Because when I go here, I know what the angle is, but when I return back, I have two ways of defining what is the angle. It is either 0 or 2 pi. So this is not a one-valued function. And this is a problem. But nevertheless, for example, if I restrict myself to the right half plane, this is a nicely defined function. So here it will be positive, here it will be negative, and it is nicely defined. Right? Let me try to compute the differential of this function, say in the right half plane. Actually, I do not have to do it in the right half plane. I can, for example, throw away this negative semi-axis, and everywhere else I have a very nice way of defining this function. Okay? I want to find the differential of this function. For this, I will use formulas that we are supposed to know. And let me compute dx. It is cosine phi dr minus r sine phi d phi, and dy, which is sine phi dr plus r cosine phi d phi. Now I want to kill these terms, so I must multiply this by sine phi, by minus sine phi, multiply this by cosine phi, and add. I will kill these terms. What I get is minus sine phi dx plus cosine phi dy equals, these terms are killed, and here I have r sine squared plus cosine squared is 1, and r d phi. So I can write d phi is what is sine phi? Sine phi is y over r, isn't it? And I have to divide by this r over r squared dx. Plus what is cosine? It is x over r, and r from here, r squared dy. So I get minus y dx plus x dy over x squared plus y. Strange. The function phi cannot be defined not only at 0, if I want to define phi at 0, I cannot do this. But it cannot be defined, for example, on the whole plane except of 0. But the differential, this form, is nicely defined at all points except of the origin. It happens. The differential has a better domain than the function phi itself. Imagine that I'm taking any curve not enclosing the origin. Yeah. And integrate d phi over gamma. What am I going to see? Since the curve does not enclose the origin, the differential is very well defined. Then, since it is not enclosing the origin, I am always able to cut my complex plane to infinity without cutting my curve. Correct? Yes? If it is not enclosing the origin, I can always cut from the origin to infinity without meeting my curve. So when I do this cut, then the function phi is nicely defined outside of the cut. And therefore, this is phi of the end minus phi of the beginning. And since the beginning and the end are the same, I get 0. So if I try to integrate this form over any curve not enclosing 0, I get 0. But the moment I try to integrate it 0, say enclosing 0 once. That's important. For example, if I do it this way, one can easily prove that it is 2 phi. Simply it is how much phi is added when I do the full term. That's it. So, and there is no contradiction, because if I enclose 0, then this form is not the differential of a function. It is not a differential of a function. So it has, there is no contradiction with what we had previously. Okay, so very interesting. This integral should be expected to be 0. It is a differential after all, correct? But sometimes it is not 0, and what is the reason for that? The function is not defined, that's it. The function is not defined, where is it supposed to be defined? The function is not defined. The Fulton suggests several simple exercises. Is the function phi well defined on the right half plane? Yes, it is. On the upper half plane? Yes, it is. On the whole plane minus, say, this line? Yes, it is. Now, is it well defined on this domain? Yes, it is. This domain is not enclosing 0. I can make a cut. It is not necessary that the cut is a straight line. I can make a cut this way, and it is well defined. More precisely, for this point, I can define the angle as I want. Then the angle is continuously extended while I am going anywhere. The only problem becomes when I come here. I do not have to cross it, because up to here I have no problems defining phi. And when I'm here, I also have no problems in defining phi. Okay? So this is everything. By the way, what if gamma encloses 0 several times? What do I have to do? There will be an integer here called the winding number, which exactly tells you how many times I enclosed the this is all. And there is one good question. Consider such x dx plus y dy, x squared plus y squared squared. Is it a differential? Definitely it cannot be differential. It is the function, if it is differential. The function cannot be defined at the origin because the differential is not defined, correct? But is it a differential of a function defined outside of the origin? Yes, it is, and one can easily guess what the function is. And I think I can guess it also. It is differential of minus 1 over x squared plus y squared. Oh, yes, it is true. Yes. You can easily check that it is indeed the differential. And therefore, what do I have? If I integrate this around any curve not passing through the origin, what do I get? 0. I get exactly 0. Now, the question they are asking is exactly the question I discussed at the beginning, one-dimensional question I discussed at the very beginning. When is this integral, when is the integral of a form independent of the path? That one has to be much more precise. Question. Consider form omega 1 form, and ask the following question. When the integral of the form is independent of the path, namely, depends only upon the endpoint, the beginning, and the end, and does not depend upon anything else. What do I have to require of this omega 1? Omega 1 is p dx plus q dy. P and q are smooth functions. Okay. What do we know about that? Our knowledge can be, so far, summed up as follows. First, if omega is df, then this is true. Then this is true. Let us analyze it a little bit. If omega is df, then it is dx at dx plus dy at dy. So p is dxf and u is dyf. Announced. From this it follows that dy d must be equal to dx q, because these are mixed partial derivatives, and in our situation of smoothness, they have to coincide. So this condition this condition actually imposes quite strong restriction on PNP. This is the restriction. And this restriction is easily verified. You only have to compute partial derivatives. It would be very nice if this restriction was, the restriction is obviously necessary, if it was also sufficient. I have to do something else here. Just a moment. No, this is not enough. Let me formulate several conditions. I put it to the... So the following simple theorem. The following are equivalent. Depends only upon the beginning and end. The integral over a closed loop is 0. And third, there exists the function f such that omega is let me prove this first, and then we can move forward. Again, this is something very easy. One, it implies to office, because if the beginning and the end are the same. So now 2 implies 1, also obvious. If you have 2 gamma 1 and gamma 2 going from the same beginning to the same end, then integral omega gamma 1 minus integral omega gamma 2 is integral omega gamma 1 and minus gamma 2. What is minus gamma 2? I reverse the direction. And this is a closed loop. And by 2, this is 0, so this equals 1. The only, okay, then now 3 implies 1.
Doesn't prove the theorem.
What?
It says it doesn't depend on the path, but it doesn't say it depends only on the beginning and on the end.
If I fix the beginning and the end and consider 2 paths,
You may have some
You're just proving that 2 implies 1.
Yeah, but you might have some invariance weirdness in the plane that the value of the integral depends on the location of some other point or some singularities in some terrace in the plane or something.
we are always, all our, everything takes place in U, in a fixed open set. And the first statement is the following. If the integral over any closed loop in the set U is 0, then the integral, then 2 integrals over 2 loops with the same in U, with the same beginning and the same end are the same. That is what I'm saying. I take any 2 loops, not loops, 2 paths with the same beginning, same end, compute their difference.
Okay.
Okay.
It doesn't prove that it depends on the difference of the values of some function.
No, it does not.
Okay.
And I don't want to. So 3 implies 1, we have proved it. If I integrate this, then the answer will be the value in the end minus value at the beginning. Okay? And the only thing I have to prove is that 1 implies 3. Then everything will go okay. And that's how we do. Fix any point, A, whatever point is. Take any point, say the function at C equal the integral from A to C omega simply. I specify only the beginning and the end, and I do not have to specify the curve, because one means that is irrelevant. Whatever. So this is indeed a function of C. This is a well-defined function. Exercise, homework exercise. Prove that dxf is P and dyf is Q, where P and Q are the coordinates of the omega. It is easy. Just by definition. Take the derivative, so from C you must move somewhere here to get a new path. So it is one line proof. And it is better to do at home when I'm not interfering. So actually these are equivalent things. So if I want this independence, then my form has to be differential. So the equation reduces to the next problem. So this is my initial equation. It is equivalent to the following equation, which omega 1 are differential. And then I need the second consideration. If a form is differential, then its coordinates must satisfy this relation. So, omega differential, then this is true. It would be nice if the reverse is true. Unfortunately not. The converse is not true. And you already know the answer. If you consider minus y dx plus x dy, x squared plus y squared, if you consider this, then d yd equals dx q. Please check it. It is one line computation. Correct? But omega is not a differential of the function outside of the origin. We have proved this because if it was, then the integral over any closed loop would have been 0, but it is not 0 for some loops, so it is not there. So there is actually, nevertheless, this is a very nice condition. And there is an obstacle for this condition to imply this fact. There is an obstacle. And this obstacle is of topological nature. What is the obstacle? If I take the complex plane, or not the complex, the plane, and erase one point, the plane is topologically not very good. That means, well, to show that it is not very good, this curve cannot be contracted to a point within this set. Okay? In other words, the first homotopy group of this set is not trivial, and so the obstacle for this to imply this is of topological reason, and it is always the case. It is always the case. In any dimension, the obstacle of condition like this to imply that this is a differential is of this sort. let me explain why. And I think I will have to finish. So, P dx plus Q dy. We can introduce the differential of this form. And this is exactly the differential which explains rho in Poincare theory. And one can easily prove that the differential is computed as follows. We will do this. dq dy, which is px dx plus py dy dx plus qx dx plus qy dy. And when I open the brackets, what do I see? It is known, I think, to everyone that dx, wedge dx, has to be 0 because this form is skew-symmetric. So I will get the following only. The only guy surviving is dx dy. And what do I get here? I have to switch them, so I will get minus py. And here I have dx dy qx. So actually, this condition can be rewritten as d omega is 0. This condition can be rewritten as d omega is 0. D omega is 0. And we are interested in integrals of omega over closed gamma. Closed gamma, correct? As I explained a little at the beginning of our today's lecture, it actually depends upon the class. So, if I have this condition, then the form is closed, and I impose the condition that this is closed. So actually, this depends upon the class of the form and the class of of gamma. But if I have a point, if I have the plane without one point, then there exist curves which are not boundaries of any domain. This curve is not a boundary of any domain in the plane without this point. Correct? If I consider this domain, it has this boundary and this is also the boundary. Isn't it? So the curve is not the boundary of this domain. So gamma is not necessarily trivial. And then what pops up? The non-degeneracy of this form. For any non-trivial gamma, you can find omega such that this integral is not 0. That's exactly what is going on. So tell me please, when this is going to imply this? When this is going to imply this? If this implies this, what does it mean? Then every gamma in my domain must be a boundary, correct? And domains where every closed curve is a boundary, these domains are called simply connected domains. So, if I have a simply connected domain, then these two conditions are indeed equivalent. So what? Again, if something is not true but we want it to be true anyway, we have to impose good conditions. So these two conditions are equivalent on a special class of domains. What are these domains? Domains for which each closed gamma is a boundary. In scientific words, it means what? That the first cohomology group is trivial, and in less sophisticated language it says that the domain is simply connected.
First homology.
First cohomology. first homology group, I'm sorry. I wanted to avoid the word homotopy because homotopy groups and homology groups are very closely related to each other, but they're not the same. There are examples where they're not the same. And here, homology groups are relevant, not homotopy. So my misstating is because I try very hard not to say the word homotopy. Okay, so far so good. Isn't it? Equation to everyone. Have I said one non-trivial word today?
Well, yeah, but we've heard it
Which one?
before.
No, the thing is that, again, I don't know, maybe we should simply skip each part, or is it okay to go like this? So,
We like
I volunteer to do a couple more, and then someone, Ilya, would you like to take over?
At some point I could, but we'll discuss it.
Okay,
Right.
very good. So since there are more than one mathematician now here,
Where is Sarah?
Sarah is actually it is